Welcome to Breadboarding. In this video, we're going to be continuing looking at the 6809 Nanocomp that we've built with the basic clock and reset circuit. We're going to be going through the data sheet for 6809 to look at what the different control signals are, which are important for running the computer. Then we're going to use the logic analyzer to look at those control signals and see what we would expect from the data sheet. And then, having looked at the logic signals, we'll then have a look at two of the signals on oscilloscope, the 4 MHz clock circuit and the reset circuit, to try and explain why some of the signals we might see in the logic analyzer may not be exactly what we would expect. So what we're going to do now, before we look at the control signals using the logic analyzer, we just need to have a look at which pins we're going to be examining and look in the data sheet to see some of the key information that we need to verify to make sure everything's working. So if you see here in the 6809, the standard 6809P data sheet, which is the one we're using, which has the two crystal signals here, what we're going to be doing is looking at one of the crystal inputs. We're going to be looking at the output enable and Q clocks. These are related to the timings of accessing the memory. We'll have a look at the read-write signal, although there won't be very much happening with read-write because at the moment we're just doing the no operation code, so it's always going to be read. Then we're also going to look at these two bus status and bus acknowledge signals, in that they may be useful for us to determine when the processor is ready to start processing instructions, and will allow us to trigger the logic analyzer with the right signals. And what we'll also be looking at is the A0 to A7 signals, just to sort of see what's going on with the processor. We don't really need to look at the higher ones. So what we're going to do first of all is to look at the next page of the sheet. And what I've done here is I've got a sheet here for identifying what voltages the processor considers low, high, and also there's a separate voltage for the reset signal. So if we look in the data sheet here, these can be quite confusing, all the various sort of VIH, VIHR labels on here. But the key thing that we're looking for here is an input voltage to be considered high, so a logic 1, for all of the input lines, and the crystal is going to be VSS, which is ground, plus 2 volts. But for the reset signal, it will be 4 volts. So in fact, the reset will only kick in at 4 volts rather than 2 volts. So it means that it will be delayed compared to all the other signals. But at the same time, we can see here the input low voltage will always be considered as a maximum of 0.8 volts. So anything below 0.8 volts will be considered low. So if we go and mark these on here, what we've got here then is an input high voltage for logic high will be a minimum of 2 volts. Let's put that there. And the reset will in fact be 4 volts. I'll mark that on there. And then the input low voltage will be 0.8 volts. So let's just put that down there. And the reason why I'm doing this is this helps to indicate how much we need to take into account the voltage levels which our logic analyzer is using to see how that might affect the signals that we're looking at. And then we also then have down here the high voltage is going to be 2.4 volts. So it's saying the minimum output voltage is always going to be 2.4 volts. So here we can then mark that as 2.4. That is the out. This is the in. And for the output voltage here, we can see that the maximum output voltage for low will be 0.5 volts. So again, this is slightly lower here. So what we can see is that that's out and this is in. What we can see here, there is a gap between what's considered the output level and the input level for a 1, and a slightly smaller gap for the inputs. So this is 0.8 and 0.5, and this is 2.4 and 2.0. And the reason why this is important is if you had any signal noise on the inputs, then between 0.8 volts and 2 volts, a voltage in that area might cause the inputs to be oscillate or to be not determined. And then finally, we have the reset voltage here is at 4 volts. So the reason why that's set at 4 volts is so that the reset line is the last signal that will become high after the power on of the system. So we've been looking at these signals here, this signal here, and this signal here. So these are the values that we're interested in. When we go on to this rather confusing diagram, this is a key diagram in that it tells us when the data will be read from the memory and when the addresses will be available on the memory. It's quite a confusing diagram. I'm not going to try and explain all of it. The key thing is here, there's a key thing down here, usable access time. And what this means is the time from when the address is available. And so the address is available on the bus from around here. So this is the address. Address is available. And then the data will be read on the falling edge of the E signal here. So this is when we read the data. Read. So in fact, this time here is the longest time that the memory has to find the particular data for the address which is being given and then to make it available in this period here before it's read over here. And we can see here the usable access time for the standard 6809 is about 695 nanoseconds. For the slightly faster version, which I think ran at 6 megahertz, it's 430. And at the 68B09, which runs at 8 megahertz, then it's quite a bit less. Now, in the early days, the memories and ROMs quite often had a 450 nanosecond access time. So you could see that on the faster processors, then in fact the memory may not have been ready to be read in time. And this is one of the reasons why there is the memory ready signals available to be able to delay access to the memory so that it can catch up. Now, it just so happens that the modern chips that I'm using have got an access time of about 150 nanoseconds, so it's not really going to be a problem. But this period of time here for 29 here, which is from this point here, is the amount of time that from the address being on the bus to being reading the data off, and then it's this change from the E signal from high to low where the data is in fact read by the processor. So if you go on to the next page, I don't think there's anything too much we need to worry about on here or on here. Right, so there's a couple of key things we need to look at here. For the power, it's saying plus 5 volts plus or minus 5%. So that means that anywhere between 5.25 and 4.75 volts. So one of the things we're looking at with the USB power supplies in my hints and tips videos is that some of the power supplies we can see that the voltage can drop once we start to draw an appreciable current, but less than the rated power rating of the power supply. And so this is something that we need to consider. Certainly anything going below 4.75 volts could potentially give us some problems. There's also some other useful information under these sections here. So for the address bus, it says it'll output a dummy address FFFF, so everything's high, and the read-write signal will be 1, and the bus status will be 0, is a dummy access or the not valid memory address cycle. So VMA is valid memory address, and the bar across it indicates not. So addresses are valid on the rising edge of Q, which is what we were looking at on this earlier page. The rising edge of Q is this area here. So this is when the address starts to be valid. And all address bus drivers are made high impedance when the output bus available is high. So this is the bus available signal here. So this is if there was direct memory access or the processor had been halted, in which case it then releases all of the address and data buses and control buses. So, and it also then tells us that each pin will drive one original TTL load or 4 LSTTL loads. So this 4 LSTTL loads is the reason why we don't need buffer chips on this initial design, just because we're never going to have more than 4 LSTTL loads active at the same time off these pins. And it's also capable of driving 90 picofarad bus. That's important because again, you'll see in the hints and tips video where the capacitance of breadboards is mentioned, and the capacitance of breadboards is typically might be 20 or 30 picofarads for the bus strips, so it's comfortably within the limits of what the processor is able to do. We can then see for the data bus, it's very similar. Each pin will drive 1 original TTL load or 4 LSTTL loads, and it's capable of driving even more capacitance on the bus. So there shouldn't be any problems with driving breadboards and the capacitance on breadboards using the chip directly. Similarly, the read-write signal, the only real issue we need to be aware of here is that the read-write is valid on the rising edge of Q, which is very similar to the rising edge of Q here. So when we come on to reset, what reset says is it has a Schmitt trigger for input greater than 1 bus cycle will reset the CPU. The Schmitt trigger is set at 4 volts, and the Schmitt trigger means that if there is a bit of noise on the line, then it won't switch from 1 to 0 very easily. It has to be a big swing in the voltage. So what this means is that the reset on the CPU will only occur at a fairly high voltage, and it won't switch back if there's a little bit of noise on the line. And what we will see when we look in the logic analyzer is that we may see that because of the voltage levels that the logic analyzer is looking for, that in fact when the reset signal is detected by the logic analyzer doesn't coincide with when the processor resets. And so what we'll be doing is having a look and seeing why that is occurring. We're not using the halt signal, we don't have to worry about that. And then the bus available and bus status. The main one that we're going to be interested in here is the bus status, because when the processor is coming out of reset, then the reset acknowledge signal will be indicated by the bus status going 1, and we'll have a look at the signals on there and we'll see how we can use that potentially to trigger the logic analyzer. Now there's a lot more diagrams and things in here. We don't really need to go through these in any great detail. What it does indicate here is the address bus, when the processor in reset state, has got the FFFE, which is the first byte of the reset vector. Once it comes out of reset, then you'll see that it's accessing FFFF, which is the second byte of the reset vector, and that when there's an invalid memory address, then in fact it would also show FFF on the address bus. And we can see later on here that with a invalid memory address, then again we see FFF. So the only times you'll see FFFF is if there's an invalid address on the bus, or as the last part of the reset sequence where it's fetching the low byte from the reset vector. Then we can also see in this later part of the data sheet, these are where the reset vectors are. So we can see, for example, that the address for the reset vector for reset is FFFF and FFFE. And the final section, we can skip over the interrupt lines. This is probably the final bit we need to worry about here. There's a little bit of information here about if we want to have an external clock, then what we can do here, rather than putting the crystal across the 2 pins, what we can do is EXTAL may be used as a TTL input level from an external timing by grounding EXTAL. So if we were to want to use an external clock, we could do so with this particular chip, and what we would do is to ground EXTAL, and we would put the TTL clock on pin 38. And then we come on to the E and Q section. So E is the main signal that we'll be using for determining bus timing. So we can see here it is the bus timing signal. Q is known as a quadrature clock. It's slightly out of phase than the E clock. The addresses on the microprocessor are valid on the rising edge, your leading edge of Q, and the data is latched on the falling edge of E. which is what I've already demonstrated on the diagram. And this is important because when we determine the control signals for accessing the memory and the RAM, then those are quite important to make sure everything's okay. The memory ready section we won't worry too much about, because this is to do with slower memory which isn't able to catch up. And then finally down here, this is the section that talks about the E and the Q signal. So it says that on the Q signal the address is valid on the rising edge here, so the address and the read-write signal is valid at that point, and then the data is read at this point here. Now, one of the things we'll look at the moment, the way how the bus signal is interpreted in the NanoComp is that the chip select signals are determined when the E signal is high. We don't take any notice of the Q signal. So what we can see here is potentially there is this region of the cycle here we're not making use of to access the memory. So if we ever had any problems accessing slower memory, we might want to consider making use of the Q signal and the E signal, because it would give us an extra quarter of a clock cycle to make use of. So this is sort of background information which, when we look in the logic probe and logic analyzer, it will just help to show where these signals come from. And this is the sort of thing that when you have problems, you're trying to diagnose things, you have to dig into the data sheet to try and work out what's going on. The final thing here is there's just a little bit here that says that about certain early versions of the chips had certain differences in the way how things work. The last 4 digits of the date code show when the part was manufactured. 4 digits represent the year and the week. So it's very small here, but this is 8012. So this means it's made in 1980 and the 12th week in 1980. In one of the other videos, I've shown that I've got some chips, I think, from 1981, 1986. Okay, so that's all we're going to do to look at in the data sheet. And what I'm going to do now is to hook up the logic analyzer to some of the control signals, and then we're going to turn on the NanoComp and just look at those control signals. And we're also going to look at the clock signals on oscilloscope to see how the difference between the logic analyzer seeing the signal and the actual physical voltage which is coming out of the pins. Right, so here's the NanoComp circuit as we saw it last time, and with the LA 2016 Kingst logic analyzer connected to it. The main difference between the previous section of the video and this one is that I've now disconnected the higher address lines, so A8 all the way up to A15, and I've now connected up the control signals we were talking about in the review of the data sheet. What I'm also going to do is I've got oscilloscope probes here. I'm just going to plug in the oscilloscope probe into the earth here, ground here, and we're going to connect this to one of the clock signals. So I'm going to plug this into the 4 megahertz clock signal, and then with the other probe what we're going to do is also look at the reset signal. So look at how the reset signal changes in time. So for that I'm just going to plug this in over on the top of the reset switch up here. Now I've got some software that comes with the oscilloscope that allows me to show some of the data on the screen, so we'll be using that in a few minutes. So this is our circuit. I have the power lead here, so I'll be plugging this power lead in and then starting the logic analyzer. So what we're going to do now is to show the logic analyzer. So here's my logic analyzer. I've got the A0 to A7 lines, but then what I've done is I've hooked up the 5-volt power supply line here, the 4 megahertz clock, the reset signal, the E and Q clock signals, the bus acknowledge and bus status, and the read-write signal, although we don't expect the read-write signal to do very much because no operation is just going to be reading the whole time. So what I'm going to do now, it's triggered on the 5-volt level, and you can see here that at the moment it's at the TTL levels, which says it's going to treat logic 1 as anything over 1.58 volts. Now you may remember the datasheet indicates anything over 2 volts will be treated as logic 1, so there's a slight difference there. So what I'm going to do now is start the logic analyzer. This is now waiting for the voltage to be applied to the circuit. So I'm just going to plug in the 5 volts. And what we can now see, if we zoom out to the whole area, what we can see here is there's a starts at 0 where the power is turned on. So you can see at the beginning here the power starts at 0. We can see there's a period of time for about 120 milliseconds before all the address buses start to do things. We can see that there's some activity on the clock signal, the 4 megahertz clock signal, and we can also see that the E and Q signals are doing something here. The reset's quite interesting in that this is a point in time when the processor seems to have come out of reset, and we can see that the bus status value here has indicated that the reset is completed. But we can see here that the reset signal on the logic analyzer appears to have shown that it's gone high after about 40 milliseconds rather than the 120 milliseconds. And this will be down to the voltages at which the logic analyzer considers things to be logic 1 versus the voltage at which the processor determines this. So what we're going to do now, first of all, is just have a look at the very beginning of the at the start. So if we look down at the beginning of the trace here, we can see as we go back to the point at 0. So this starts at 0. You can see that the 5 volts is where we've triggered this, and so we're not really looking at anything before that. For the first couple of milliseconds, we can see that the available bus status signals are high, so the processor won't be doing anything with the buses. We can see here that the clock signal, although it's only showing in the logic probe as doing something at this point in time, and we can see here if we look on the top right hand side here for the frequency, that in the early stages it's showing as only 1 megahertz, but then a little bit later on it's now showing as 4 megahertz. So there's a period of time for the clock to stabilize after power on. But we can also see down here that the E and Q signals are actually running at 1 megahertz, and these seem to be fairly stable quite early on. So again, what the issue here is likely to be is the voltage level on the clock signal here is quite low, and so it takes a while for the logic analyzer to be able to pick that up and for it to stabilize. So if we now zoom out, we can see that after a period of time, and if we measure here, we can see that it's approximately about 120, 127 milliseconds that the address bus starts to cycle. So this is, we zoom in to this level here. So this is the point at where the processor is coming out of reset. So you can see that the bus status has indicated that the reset is ending, and after this point in time then the address bus starts to cycle, and we can see here that it was originally FEFF, which is where the reset vector is coming, and then starts with 12, 13, 14, 15, which, as we explained in the previous video, the no operation code is 12 hex, and so this is the value that will be provided for the reset vector. So the first address that will be loaded is 1212 hex, and then it will go on to the next one. And we can see here the address bus increasing. Now, when we get down to this level here, we can now see where the clock signal is. So this is a 4 megahertz clock. If we look at the top right hand side here, we see frequency 4 megahertz, but the duty cycle is 32%. So the duration of the high logic level is shorter than the low logic level. And when we look at the oscilloscope, we'll see where that perhaps comes from. And then down at the bottom here, the Q signal and the E signal are generated off the 4 megahertz signal here. But if we look at E, we can see that's 1 megahertz, and so is the Q signal is also E, but they are out of phase by about half a clock signal. And in fact, if we put our we want to measure that, we can measure the difference between here and here. So the difference there is about 240 nanoseconds. So this gap here is 240 nanoseconds. If we see how long each individual, so half a cycle there is about 495 nanoseconds, and the full cycle here is about 1 microsecond. Oops, just that back. You can see here that it's 1 microsecond, that thing, but they're about a quarter of a cycle out of phase. What this indicates to us is that if we want to trigger our logic analyzer to see when to start collecting signals when the processor comes out of the reset state, then in fact looking for a rising signal on the bus status would actually be quite a good way of doing this. And the reason being that the reset signal itself is not a very reliable way of doing things, because we can see that with the logic analyzer, the reset signal starts to be treated as logic 1 sometime after about 45 milliseconds, when in fact the system doesn't actually come out of reset until about 127 milliseconds. So the reason for looking at this is to make sure we find what the right signals are that we're going to look at. And obviously going forward, we're only going to be using the E signal for determining the memory access clock. But should we want to use faster processors and have problems with accessing slower memory, then in fact we might want to consider using the Q and the E clock to gain access to this. So hopefully this shows that these signals are important, and when you're trying to troubleshoot the reason why something may not be working, taking into account what the voltage levels are that the processor takes as being ones and zeros, what the test equipment you're using treats as a 1 and 0 can have quite a large effect. Now what I'm going to do now is just have a quick look at the oscilloscope signals for the clock signal. So we'll be looking at the clock signal here. We can see our clock signal here, which is 4 megahertz, but the width of the high value and the low values, 170 nanoseconds and 80 nanoseconds, so a duty cycle of about 32-33%. So what I have here is the oscilloscope software for my Hanmatech DOS 1102 oscilloscope, and what this is showing is one of the clock signals, and we can see down the bottom here 4 megahertz signal. The period is 0.250 microseconds, so 250 nanoseconds, and that the peak to peak signal is just over 2 volts. So this will be explaining one reason why the duty cycle picked up in the logic analyzer will not be 50%, for example, because the logic analyzer, I have marked on here a line, this line here marks 1.58 volts, which is what the logic analyzer is treating as logic 1. So you can see here that where the clock signal goes above logic, goes to logic 1, only accounts for approximately about 167 nanoseconds out of 250 nanoseconds. So if we see what 168 nanoseconds divided by 250 nanoseconds, we'd expect this to be around about 60 or 70%. Yeah, so we can see that accounts for 67%. So if you reverse that, then that is about 32, 33 duty cycle, which I think is what we saw in the clock here. Yeah, it's about 32%. So that really explains why the clock signal here, we're seeing this 34% duty cycle up in the top right hand side here, is because our logic analyzer is treating logic 1 as anything over 1.58 volts, and what this indicates here is that this is only occurring for this period of time. So that explains the reason why our clock signal is appearing with this duty cycle. So what we've done here is recorded on the oscilloscope trace the reset signal. So you can see here, this is normal running, so the reset would be at 5 volts. So these are 1 volt per division. So we've got 1, 2, 3, 4, 5 volts. Then we press the reset button for a few, half a second or so. Then we release it, and we can see here that the resistor and capacitor allow this then to charge back up to close to 5 volts. Now what I've done here is put some measuring lines on here, so we can see here that the signal level here from here to here is shown in the delta. So what I've done here is shown where the delta in the voltage is 4 volts. So this is what the data sheet says that the microprocessor should come out of reset state when the reset signal gets to 4 volts. But then what I've done is then measured how long it takes on the y-axis here between the start of the coming out of reset and then the end of it where it crosses 4 volts. And what you can see here is that this is actually 227 milliseconds. If we go back to the main in the main logic analyzer output, we can see here that in fact the time between the reset, between the power coming on the reset, is about 125, 127 milliseconds. So that's quite a bit different from the value that we're seeing here. So if we go back into here, so we see 227 milliseconds rather than about 125, 127 milliseconds. Now, if we move this bar down and say, well, let's move it to about 123 milliseconds, let's see what the voltage is around then. So if you see here, we're now moving it down. You see the figure dx on the right here. We'll move it down to about 127. So you can see here that in fact that 127 milliseconds, which is much closer to the observed delay between the power coming on and processor coming out of reset, and this voltage is in fact 123 volts. So in fact it would appear that this particular microprocessor is coming out of the reset state at around 3 volts rather than 4 volts on the basis of this particular time constant. And if we plug in these values, so we know that we've got 5 volts here, 22 microfarad capacitor, a 5.6k resistance, this gives a time constant of approximately 0.123 seconds or 123 milliseconds, which would certainly tie in with the time that we see in the logic analyzer here. So this time to come out of the reset state is about 127 milliseconds. So it's very, very close within tolerance. And if we see here, we can also then see it at various times. So at 1 times the time constant, we expect to be about 63% of the overall voltage. So 63% of 5 volts is just over 3 volts. So it would appear that the processor is coming out of the reset state at 3 volts and not 4 volts, which is what the data sheet said. Now this could be because this is a very old microprocessor, it's from 1981. There could be other reasons for it, but at least it helps to explain what's going on here. So you can see that the processor comes out of reset state at some voltage between about 3 and 4 volts, and then carries on operating as per normal after that. So in this video, we've reviewed the datasheet for the 6809 and tried to understand what the control signals are that are used by the computer. We've looked at the logic analyzer and the oscilloscope output to understand what the signals we're seeing and how the voltage level on the analyzer can affect the signals we see and display. In the next video, we're going to be looking at the existing ROM chip from the original 1981 NanoComp. We're going to be using an EPROM programmer to read that and then to burn that into a new EPROM, then hooking up the EPROM and the RAM onto the NanoComp circuit and to see the monitor load and the expected signals on the ROM and the RAM. as the monitor initializes.